A car of mass 1,100 kilograms lands on its brakes and the wheels lock up and the car skids to a stop in 2.2 seconds, and the car is traveling at 18 meters per second at the moment brakes are first applied. We need to calculate the acceleration of the car and then frictional force that opposes the car's motion and how far does the car travel. This is a simple problem, but we should understand how to approach a question systematically, because later you're going to do more advanced problems. So you need to understand basic steps and how to approach the question. So we are going to first visualize the problem, and I'm going to start with the free body diagram. So in the free body diagram, you should show all the forces acting on the object. I'm going to assume that the car is moving to the right. I'm going to start off by defining the coordinates. Positive x is to the right and positive y is up. So I'm going to use dotted lines to show the x-axis and y-axis, and the object is shown as a point mass, and the forces acting on the car. So let's look at the normal force. Normal force should act up because the road is pushing the tires of the car up. So that is the normal force from the road. It's acting up. And the next force is the weight. So weight is always directly downwards, but look at the relative magnitudes. The normal force should equal in magnitude to the weight because the car is moving in x direction. There is no net force in y direction. So for that reason, the magnitude of the normal force is equal to the magnitude of the weight. And then the friction force opposes the motion. And since the wheels are locked up, the force from the car's engine is just zero. There's only one force acting in x direction, that is the kinetic friction, because the car is in motion. So now let's see the knowns and unknowns. So we know the initial velocity when the car first starts to skid is 18 meters per second, and then the car stops. That means the final velocity is 0, and it takes 2.2 seconds to come to a stop, and the mass of the car is 1,100 kilograms, and again we have specified the coordinates, and we are trying to calculate the acceleration of the car, and the acceleration is in x direction because the car is moving in x direction. So we expect a negative value for the acceleration because the net force is acting to the left, and kinetic friction is acting to the left, but we are only interested in magnitude of the kinetic friction. And the third is we are trying to find the final position. The car is moving to the right, the final position should be a positive. Now the applicable concepts, this is based on chapter 4, but you will have to use your knowledge from chapter 2 and chapter 4 when solving part A, B, and C. Okay, so now we are going to plan a solution. When we plan a solution, I'm going to make a chart to identify each force and then x and y component of each force. So first force is the normal force, and the x component of the normal force is 0 because it's acting in y direction, and it's positive because it's acting up. And the second force is the weight, and weight is acting in y direction. So again, there's no component in the x direction, that would be just 0, and then it's negative because weight is acting directly downwards. And then kinetic friction, friction always opposes the motion. Since the object is moving to the right, friction should act to the left, so it's negative. And then the y component of the friction is just 0. And then let's look at the first equation we are going to use. we're going to use the final velocity is equal to initial velocity plus acceleration times time. We know everything except for the acceleration, so we can use that to solve for the acceleration in x direction. And then we need to calculate the magnitude of the friction. Let's use Newton's second law, and let's use the component form of the Newton's second law, because we are interested in the forces acting in x direction, because the acceleration in x direction and object is moving in x direction, and also the kinetic friction is acting in x direction. Okay, so next we need to calculate the final position. For that, we are going to use this equation. We know everything except for the final position. Okay, so we have a plan. Now next step is to execute this plan. So let's do part A first. I'm going to use the equation and do the substitution. Initial velocity 18 meters per second. It's positive because object is moving to the right. And acceleration is an unknown, times time is 2.2 seconds. And if you separate the acceleration in one side of the equation, you will get this is negative 18 meters per second divided by 2.2 seconds. You will get negative 8.18 meters per second squared. As we expected, acceleration is to the left. That means object is slowing down while it's moving to the right. Okay, so for part B, we are trying to calculate the kinetic friction. So for that, let's use Newton's second law, and this chart is really helpful, guys, because now you can just look at the x component column and just put all the forces acting in the x direction. This is a simple case. You just have one force acting in x direction. The kinetic friction is equal to mass times acceleration, and then you have the acceleration from part A. Do the substitution, and when you solve for the kinetic friction, you will get 8,998 newtons. If you round this to nearest 10, you will get 9,000 newtons, but not required. Just you can leave it as this. And now you will you might be wondering, how did I put newtons there? Because the SI base unit of newtons is kilogram meters per second squared. That's why we have newtons for the unit of kinetic friction. And for part C, we're trying to calculate the final position, or how far did the car move. And so let's see, initial position plus initial velocity times time plus half times acceleration t squared, and then initial position is 0, and then the initial velocity 18 meters per second, and then times time plus half at squared. So guys, I'm running out of space here. I'm going to write it on the next line, but I think you get the idea. You have to multiply 2.2 seconds squared, and so I'm going to repeat the step again. Times time squared. So for the final position, you will get 19.8 meters. So that's how far the car traveled. And then we solve for the acceleration, and we have the kinetic friction. And is the solution complete? Yes, the sign of the answer is correct. We got what we expected. There's correct units, and then magnitude of the answer is reasonable. And let's just see what we did. So we started by visualizing the problem. We have the free body diagram. We paid attention to relative magnitudes of the forces, and we defined the positive x and positive y axis. We identified the knowns and unknowns, very important. And then we made this chart to identify the x and y components of each force. And then we executed the plan. That's it. Please understand the process.